Hello everyone. In this week's lecture, we will cover trip generation modeling as the first main step in the four-step travel demand modeling framework. In trip generation modeling, we develop a relationship between the number of trips produced by or attracted to a zone and the characteristics of the zone, mainly land use characteristics, number of jobs, number of population in that zone. In the trip generation modeling step, or wider in the travel demand modeling framework, a trip is defined as travel between two places of activity. Trip productions are trips generated by residential zones to serve a need, and as opposed to productions, trip attractions are trips generated by activities such as employment, retail, recreational activities that are related to satisfaction of a need. So when we talk about trips, we have productions and attractions. We can further classify trips by trip purpose. Trips can be home-based trips or non-home-based. Home-based trips refer to the trips that one end of the trip is at home. Note that only one end is sufficient to call a trip home-based trip. Home could be the origin of the trip or the destination of the trip. For example, we will have home-based work trips, home-based shopping trips, home-based school trips. Non-home-based trips refer to the trips that neither end of the trips is at home. For example, a trip from work to shopping or a trip from shopping to gym. None of the end of the trips is at home, so we call them non-home-based trips. Trips can be further classified by time of day. We can classify them into peak and off-peak periods. And proportion of the trips by different purposes varies greatly with time of day. So here is a real example of the percentage of the number of trips for different purposes and at different times of day, AM peak, morning peak, and off peak. For example, you can have a look that 52% of work-related trips happen in the morning peak, while it only constituted of 12% during the off-peak period. If you look at the return to home trips, the last purpose in the table, you can see in the morning it's only 2.7%, while during the off-peak period it's more than 41% of the trips are related to returning to home. Further classification of trips can be done by the socioeconomic characteristics of the trip maker or traveler. For example, trips can be classified by the income level of the traveler, car ownership status of the traveler, or household size and structure of the traveler. So now think of 5 levels of income, 3 levels of car ownership, and 6 classes for household size. How many classes will we have in total? Obviously, 5 multiplied 3 multiplied by 6 will give us 90 different classes of trips. Next, we will discuss what factors actually affect trip generation. For trip production, factors such as population, income, car ownership status, quality of transport facilities, and frequency of service within the zone, residential density, household age structure, or stage in the family life cycle are the important factors that could affect the number of trips that get produced in a zone. Factors that affect trip attraction usually include employment levels, classified by type of employment, educational institution enrollment, floor space of retail, and accessibility provided by the transport system, and etc. Freight trips are also very important that are usually gets overlooked in travel demand modeling. Freight trips usually amount to 20% of all journeys. Well, this is not a fixed number. It obviously depends on the location, the city, what part of the country you're looking at. But important factors that affect number of freight trips include number of employees, number of sales, total area of a firm or the production plant in a region, and other factors related to manufacturing and production of goods. There are different types of trip generation modeling that we will cover in this week. Growth factor, regression modeling, and cross-classification are the three commonly used methods in trip generation modeling. Growth factor works by increasing or decreasing number of trips by a factor. It's very simple, but it's naive. Regression modeling estimates the parameters of an underlying model relating the number of trips from a zone to the characteristics of the zone. And it's purely a statistical method. Cross-classification usually considers households and categorize them on the basis of general characteristics such as car ownership status of the household, household size and age structure, and a trip rate is finally calculated for each category. So what we do in the trip cross-classification method is we look at each zone and then we look at each household classes that we have defined, and we try to estimate a trip rate or the number of trips that are going to be made by that specific household class per day in different categories. For example, a category that has a low car ownership, large household size, and similar other categories. In the growth factor method, the basic equation is that you multiply a growth factor to the existing trip rate of the base year to get the trip rate in the horizon year. So in this equation, Ti will be equal to Fi T small I, where the T capital I is the future trips in zone I, T small I is current trips in the zone I, and Fi is the growth factor for zone I. But how can we get this growth factor? The growth factor is usually a function of population, income, or car ownership of the design or base year and the future year. So, for example, in this case, we are defining the growth factor Fi as a function of the population P, income I, and car ownership rate of the future year, the horizon year, or the design time period, over a function of the same variables, population, income, and car ownership of the current year or the base year. I think it's now a good time to have a look at activity 4.1 to get a better sense of how growth factor method works. In activity 4.1, we will go over the first example of chapter 4 of the textbook. Consider a zone with 250 households with car and 250 households without car. Assuming we know the average trip generation rates of each group, being households with a car produces 6 trips per day, and households with no car produce 2.5 trips per day. We can easily calculate the current number of trips per day, therefore. So we have 250 households with no car multiplied by their trip rate, which is 2.5 trips per day, plus 250 households with a car, and they generate 6 trips per day. Therefore, we will have a total of 2,125 trips per day for that specific zone. Let us also assume that in future, all households will have a car. Therefore, assuming that income and population remain constant, we could estimate a simple growth factor as below. So a growth factor that only depends on the car ownership rate. So we define the growth factor as the car ownership rate of the future year over the car ownership rate of the current year. Therefore, 100% of households in the future, we assume that they will have a car, over 50% of the households having a car in the current year. Therefore, the growth factor will be 2. Now, if we apply this growth factor 2 that we estimated based on the car ownership rate, we multiply this 2 by the number of trips per day that we calculated, we will get a total of 4,250 trips per day for the future. But I guess by now you could tell that this is a very crude method. If we use our information about average trip rates and make the assumption that these will remain constant, we could estimate the future number of trips in another way. So let's have a look at the number of trips. We had a total of 500 households, and we assume that in future all of them will have a car. And we know that that a household with a car will generate 6 trips per day. So we have 500 households with a car in future, multiply the constant trip rate of 6 trips per day, we will get 3,000 trips per day in future for that zone, while previously we estimated 4,250 trips per day. So you can see that the gross factor method overestimates the total number of trips in this example by approximately 42%. This is very serious because trip generation is the first stage of the modeling process, and whatever error we produce in our calculation or estimation here will be carried through the entire process of the 4-step model and may invalidate the work on the subsequent stages. So in this activity, we learned that the gross factor method is very crude and it may generate large errors. In practice, the gross factor is only used to predict the future number of external trips. External trips are the trips coming or going to some external zones that are not considered in a travel demand model. For example, trips that are coming from another city to your city of interest, or trips related to tourism. In the regression modeling method, we estimate the parameters of a model relating the number of trips produced in a zone to the characteristics of the zone, using a linear regression or a nonlinear regression. So in this example, we formulated the linear regression as the expected number of trips generated at zone I equals to a linear function of set of variables of interest, xi, like population, employment, etc. So in a regression modeling framework, we estimate this A and B. So here is an estimated example of a linear model at a household level for home-based trips, where TH is the number of person trips for household H. The first number in the linear regression estimated is a constant in the model. Then we have number of persons in the household, then number of children under age 5 in the household, number of workers in the household, and at the end we'll have number of cars available in the household. So what we do in the regression modeling method, we estimate the coefficients behind these parameters that we consider. We usually do that using data from household travel surveys. So for a zone that have a certain number of people in a household, as an average rate, for example, the average number of children in a household, number of workers, and number of cars in the household, you can estimate the number of trips. But what does this constant is for? If you make all the variables 0, meaning that there's no one in the household, no children under 5 in the household, no worker in the household, and no cars in the household, you still get half a trip. Well, this is only for the statistical reasons that we leave it to get a good goodness of fit. Otherwise, it doesn't make sense for a household that no one lives in it. Half a trip will get generated. There are several statistical tests that we can use to make sure the estimated regression model of trip generation is a good one. Please note that the regression model is not always linear. You can estimate a nonlinear regression model. You can apply logic tests, which basically refers to investigating the sign and magnitude of the estimated coefficients to see whether they make sense. You can have a look at some goodness of fit measures like R-square, which is a commonly used measure. And there are also some other statistical tests such as F-test to compare different models to see whether model A is better than model B. So a little bit more information about the F-test. For example, we have two models, model 1 and model 2. Model 1 is a restricted model, meaning that it has less variables, while model 2 is unrestricted with more variables included in the model. We can then calculate the F value using this formulation, which is using the residual sum of the squares of the first model, of the restricted model, minus the residual sum of the squares of the unrestricted model, over the subtraction of the number of parameters in the second model versus number of parameters in the first model. And we divide this value over residual sum of the squares of the unrestricted model divided by the number of data points you have minus the number of parameters in the unrestricted model. So in the F-test, the null hypothesis is that model 2, or the unrestricted model, the model with more variables, does not provide a significantly better fit than model 1, or the model with less variable. Therefore, we reject the null hypothesis if the F value is greater than the critical value. So when you estimate model 1 and model 2 in any case, you calculate the F value, you check whether it is greater than the critical value. If it is greater than the critical value, you reject this null hypothesis. That means model 2 is not necessarily better than the model 1, the one with less variables. So we stick to the model with less variables. I think it's a good time to have a look at activity 4.2 to practice a little bit on trip generation using regression modeling. In activity 4.2, we go over example 4.3 of the textbook. Consider the variables trip per household y, number of workers x1, and number of cars x2. The table you see here presents the results of successive steps of a stepwise model estimation. The last row shows values for the t ratios for the estimated coefficients. Assuming large sample size, the appropriate number of degrees of freedom is also a large number, so the t values may be compared with the critical value of 1.645 for a 95% significance level on a one-tail test. We know the null hypothesis is unilateral in this case, as y should increase with both x1 and x2. So what you see in this table is three different linear regression models. The first one only includes one variable, number of workers, to estimate trip rates. And we have an R-square of 0.203. The second model includes both x1 and x2, number of workers and number of cars, and the R-square value is 0.325. And the last model not only includes the two variables of number of workers and number of cars, but it also includes a constant in the model. And the R-square is 0.384. And the t values you see here are to test whether the estimated coefficients are statistically significant, because all the estimated t values are greater than the critical value of 1.6, we can say that the estimated coefficients are statistically significant. But among these three models, which one is the best? Which one should we select? Well, perhaps the first thing to do is have a look at the R-squares. We can see that the last model has the largest R-square compared to the other values. It's still a fairly small R-square, but this is very common in the travel demand modeling context. We don't necessarily get high R-square values. Then look at the coefficients and whether to see whether they make sense. Both number of workers and number of cars in the last model and the model before have positive signs. And it makes sense. If the number of workers increases, if the number of cars increases, you expect to see higher number of trips per household. So this is also good. Perhaps to compare Model 2 and Model 3, one would like an additional test using the F-test to see whether inclusion of this additional constant significantly help the goodness of fit of the model. That's what actually F-test does, as we talked about. Another way of looking at the goodness of fit of such models is to look at the individual residuals for each category or for each case. So in table 4, what we do is we actually compare the predicted value using the last model versus the observed value in the data. So for example, for the case of a household with no car and no workers in the household, the observed value was 0.9 trips per household, and the model also estimates 0.9 trips per household. For another case, let's have a look at household with 2 or more cars and 2 workers in the household. The observed trip rate value was 4.7, while the predicted value using the regression model was 6. There is larger error in this specific category compared to the 0, category. So this is a good way to have to look at in what categories and in what cases the model is not performing as good as the general or average case. The last method that we cover in this week is the cross-classification method. There are 2 main steps in the cross-classification method. In the first step, we group the households by the desired characteristics. For example, number of persons in the household, number of workers, or car ownership. After grouping the households into different categories, we calculate a trip rate for each category based on some survey data. And then to predict the future number of trips for a zone, we determine the number of households in each category as we defined. We multiply the appropriate trip rate, the estimated trip rate, by the number of households in that category. And then we sum all the number of trips across all categories to obtain an estimate of the total number of trips in that zone. So for example, here is a real cross-classification data obtained from a study done by Federal Highway Administration in the US in 1975 from a city, Madison, Wisconsin in the US. So you can see that the cross-classification is based on 2 variables only, the family size and number of cars owned by the household. Family size changes from 1 to 5 and cars owned changes from 0 to 2 plus. So there are 3 multiplied by 5, 15 categories specified. So using some survey data, we estimate the average trip rate in each category. For example, for households that have 2 members with no car, the average trip rate was estimated as 1.5 trips per day, versus a household with 4 members and 1 car, they make 8 trips per day. There are certain limitations of cross-classification method. First, it ignores the within category variances, even though the majority of variation arises from variation within rather than between cells. So for example, in this example, not necessarily all the households within each category make the same number of trips as the average. For example, in this case where we had 2 members in the household and no car, maybe some households make 2 trips, maybe some make 3 trips, maybe some make half a trip, but the average is 1.5. So this method, this cross-classification method, cannot really capture the variation inside each category. The second limitation is related to the accuracy of the estimates of trip rates, because in cross-classification method, that accuracy only depends on the number of households in each cell. So if we have few number of households in a cell, for example, for the category that includes families with 5 members and 2 plus cars, if there are only few households in this category, that number is not really reliable. And the last limitation that we cover is the difficulty to account for land use and accessibility factors, because these factors are usually difficult to divide into meaningful ranges and classes. Therefore, the estimated trip rates for each categories will be only based on some characteristics of the household rather than characteristics of the transportation system itself. There are also some limitations in the existing trip generation models in practice. There is an absence of variables which can reflect changes in the transport system or service. There is less accuracy in trip attraction models than trip generation models because we don't yet have a very well understanding of destination choice behavior of travelers. And as I briefly talked about, freight trips are rarely included in demand analysis model. I believe it's now a good time for you to have a look at activity 4.3, 4.4, and 4.5. I'd like you to go over each activity, spend time on it, think about it, read it, and solve the problems included in the activities.